morning. Last class we had discussed uh, geometric representation of signals after discussing about Gram Schmidt procedure to find the independent variables phi 1, phi 2. So they are all linearly independent orthonormal basis functions. Remember, the set phi 1, phi 2 and all are all linearly independent orthonormal basis functions. We were discussing how to find those values, how to find the values of the basis functions phi 1, phi 2, so on till phi n. And we also discussed how to find the values of their coefficients Sij. So given I varies from 1 to m and j varies from 1 to n. So how do we find these two values we discussed? And then we also said we can geometrically represent each signal as a signal vector Si. So the given finite energy signal Si of t can be represented as a vector Si, and each vector will have n coefficients Si1 to Sin. Okay, and this I value will range from 1 to m, representing m message signals. These vectors could be drawn geometrically in a signal space diagram, also known as the constellation diagram. So what is this constellation diagram? In this, we geometrically represent the signals as using the orthonormal basis functions phi 1, phi 2, phi 3, so on. And once we have those basis functions, we will be drawing these signals in that is known as the signal constellation diagram. We will be using this diagram commonly later on to find the Euclidean distance between two signals, to find the decision-making boundary. So in a receiver, if I should differentiate between received signal as S1 or S3, I should have a decision boundary between the two. Are you following what I'm telling? So, sorry. Just a minute. Yeah. So if at all you should be able to differentiate between two received signals, you should have a definite boundary between the two. Suppose say I have to differentiate between S1 and S2. I'm supposed to have a boundary here. I'm supposed to have one decision boundary between these two, and all the values of voltages which come below this are treated as S3, and all the values which come above this boundary are treated as S1, something like that. So all this geometrical representation will be helpful for us in deciding what is the received signal and how to go about it. Okay. So when we are working with receivers, it's very important that we have this constellation diagram. And if I'm able to find the Euclidean distance between two signal points, even that will help us in finding this boundary. So finding the Euclidean distance, finding the distance between these 2 points, okay, which is called Euclidean distance, will help us in what? Drawing. This will help you in drawing a decision boundary, at the receiver to differentiate between two received signals. So it depends on the spacing. If signals are closely spaced like this, it becomes quite difficult for us to differentiate between the two. But if the signals are far spaced, say for example S2 and S3 are quite far off from each other, In such cases, drawing the decision boundary and identifying whether the received signal was S2 or S3 will not be so difficult. And you should also remember one thing. There will be noise added to the signal. Here we have just plotted the signal as it is, but when noise gets added to the signal, what happens? This S1 may be here, this it may be shifted here. So S1 may be here or here, that S1 dash may be the received signal I'm talking of. That S1 dash can be somewhere here. I'm calling it as S1 dash, the received signal. So the received signal need not exactly be same as S1, but it will be slightly different. And because of noise being added to this signal at the channel, this point can be shifted either here, 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 anywhere. Now say for example, if the point is here and it is below this decision boundary, you have drawn a decision boundary between S1 and S3 and you see the received S1 dash has come below the decision boundary. So what will the receiver think? The receiver will decode this S1 dash as S3. It considers all the signal points which is coming below this decision boundary to be S3, and because of noise effect, if S1 has been received as S1 dash and it has fallen below the decision boundary, the receiver will decode this S1 dash as S3 rather than S1. So that is an error in decoding. It's an error in reception which should be avoided. Hope you understood the importance of this signal space diagram or the constellation diagram. So this signal space diagram is a easy geometric representation of the transmitted signals, which are defined in terms of linear equations of orthonormal basis functions. So we know that each signal is represented as a linear equation of a combination of orthonormal basis functions. So for everything, I have a combination of orthonormal basis functions like this. So it's a linear equation. Every signal is a linear equation. And these signals we are representing in this signal space diagram. And what is the use of doing this representation? We'll find the Euclidean distance between the different signals in this signal space diagram, and using that distance we will take the midpoint and draw a decision boundary so that the receiver will be able to decide all values of the received signal which lies below that boundary are bound to be one particular signal, say S3, above that another signal S1, and I'll have one more boundary here. I can have one more decision boundary between S2 and S1, and anything to the left of this is treated as S2, anything to the right of this is treated as S1, something like that. So this is how we analyze the receivers and we'll be able to decode the signals. And one thing which you should surely remember, though you have transmitted the signal as S2, the constellation point will not be exactly there. That S2 can be distributed anywhere like this because of noise. So S2 dash or S2 cap, whatever you want, you call it as, it can be distributed anywhere in this diagram because of addition of noise. If the noise is less, it will be close to the actual point. Whereas if the noise is more, it will be somewhere farther away from the actual point. Is this concept clear? We also did a problem. You have to give me some answers. If it's not clear, please ask. You're always welcome to ask doubts. It will be useful to others also. So we took a problem and we solved yesterday showing how to plot this signal space diagram or constellation diagram, how to identify the signal points, and also how to define the signal as a linear equation. We'll take up some more problems on this, and usage of the Gram Schmidt procedure, orthogonalization procedure. Let me take down the second problem. Consider a signal space with basis functions phi1 and phi2 as given below. Please write down. Let me say phi1 is represented like this. Its value is 1 by root 2 in the interval 0 to 2, and phi2 is represented as 1 by root 2 in the interval 0 to 1 and minus 1 by root 2 in the interval 1 to 2. Okay. Now he is asking us to plot the signal S of t with coordinates 2, 2. So what does this mean? This means that the signal S of t, what does it mean? Given the signal S of t is defined as, how many orthonormal basis functions are there here? He says the signal space has two orthonormal basis functions, phi1 and phi2. And remember, what are the axes in the signal space diagram? The axes in the signal space diagram are the orthonormal basis functions, phi1 and phi2. So it's a two-dimensional signal space diagram because it has two orthonormal basis functions. Now, if S of t has coordinates 2, 2, how do I define the equation? Linear combination of orthonormal basis functions. So it is given that S of t is given as 2 times phi1 of t plus 2 times phi2 of t. Is that clear? Please understand how to write the representation from the coordinates to the equation and back. So this is given. Now all what we have to do is we have to draw the constellation, or we have to draw the signal. Here it's not the constellation, you have to plot the signal S of t. So let me consider, since phi1 is known and phi2 is known, all I have to do is I have to find 2 phi1 and 2 phi2 and add both to get the signal. So we'll do it geometrically only with phi1 of t as shown above. What would 2 phi1 of t be? Can you draw the signal 2 phi1 of t? What should you do? Take phi1 of t and multiply it with 2. So the value of phi1 of t is 1 by root 2 in the interval 0 to 2. What will happen if I multiply 1 by root 2 with 2? 2 into 1 by root 2 is how much? Its value is root 2. So 2 into 1 by root 2, the value will be root 2. So I have plotted the signal 2 times phi1 of t. Similarly, let me plot the signal below this itself so that it will be easy for me to add. I have to plot the signal 2 times phi2 of t. Let's have a look at phi 2 of t. Its value, it's like a square wave having amplitude plus 1 by root 2 between 0 to 1 and minus 1 by root 2 between 1 to 2. So both the values I should multiply it with 2. Yes or no? It is 2 phi 2 which I am trying to get. So both the magnitudes I'll multiply with 2. So here I should mark this midpoint 1 also, and I need 2. So this value will be 2 into 1 by root 2, which will be root 2. And this value will be minus 1 by root 2 into 2, which will be minus root 2. Correct? See, these are simple things. Keep following. When I'm doing in a hurry, there may be chances of making some mistakes in calculation. Please be alert. Any changes in this? So all what we have done is, first we have defined the signal S of t because he has given us the coordinates, and now we are trying to find the plot of this signal S of t. Using phi 1 and phi 2, we have defined 2 phi 1 and 2 phi 2. Finally, how do I represent the signal S of t? It is 2 phi 1 of t plus 2 phi 2 of t. You just have to add these two. Can you tell me what will you get? S of t is 2 phi 1 plus 2 phi 2. It's all just graphical. It's easier to do it like this than consider the signal. So between 0 to 1, it is root 2 plus root 2. Yes or no? What will I get? The value is 2 times root 2. Root 2 added to root 2 between 0 to 1. So the value becomes 2 root 2. And between 1 to 2, it is root 2 minus of root 2. So the value remains 0. Is this clear? So the signal S of t will have the value 2 root 2 in the interval 0 to 1. And in the interval 1 to 2, it will have the value as 0. Yes. Hence, this is the plot of the signal S of t, and we are done with the solution. So, such simple problems also can be asked for 3 to 4 marks, or you can have it a little more complicated. Anyway, let's try to take up some more different types of problems and analyze. Any doubts with this? Do you have any doubts with this?
No, ma'am.
Yeah, take down the next problem then. Applying the Gram Schmidt orthogonalization procedure. Applying the Gram Schmidt orthogonalization procedure. Find a set of orthonormal basis functions. Find a set of orthonormal basis functions from, this is functions, FNS I have used, from the given set of signals below, given set of signals shown below. We are going to draw those signals. Also express the signals as a linear combination express the signals as a linear combination of the basis functions and draw the constellation diagram, signal space or constellation diagram. Okay, so this is a little more extra than what we have done before. So he's asking you to apply the Gram Schmidt orthogonalization procedure and first find the value of the basis functions. Remember phi 1, phi 2 orthonormal basis functions you should find first, and then you have to express the given signals as a linear equation of those basis functions, and then also draw the constellation diagram representing the signals. Okay, so what are the given signals? How they are? I'll plot the signals. There are three signals given: x1 of t in the interval 0 to 4 having value as 3. The value of x1 of t is 3 in the interval from 0 to 4. Next we have x2 of t. x2 of t is given as having the value 3 in the interval 0 to 2, half the time period as the first one. And then we have x3 of t, the third signal. Instead of the signals being named as S1, S2, S3, here they are named as X1, X2, S3, X3. So this signal exists between 2 to 4 and it has the value 3 in this time interval. Okay, so these are the given three signals. Now you have to find the orthonormal basis functions for this and all that. Now looking at these three signals, can you tell me which two signals can be considered as linearly independent and which is dependent? Look at the three signals and tell me. See, when do you say a signal is independent? When you can't express it in terms of the other signals. So that's what you're supposed to look for. Just see if you can write one signal in terms of the other signals. Can I write any one signal in terms of other signals here? Or one simple, you say, solution. It can be observed that what? Please be attentive and answer something. Can't, looking at x1, x2 and x3, can't you clearly see x1 can be obtained as x2 plus x3? Yes or no? I can easily see here looking at the representation of the three signals here. See, this x2 has the value 3 between 0 to 2. x3 has the value 3 between 2 to 4. Whereas x1 has the value 3 between 0 to 4. So if I add x2 with x3, I will easily get x1. So here x1 is dependent. I can write it. Whereas x2 and x3 can be considered as linearly independent signals. You say, therefore, x2 of t and x3 of t can be considered as linearly independent signals. Therefore, their there should exist two basis functions, two orthonormal basis functions. So usually this is a clue to tell us how many basis functions should exist. If I have two independent signals, it can be two orthonormal basis functions in as a general rule. Okay. Also, we know that what? If x1 and x2 are independent, if x2 and x3 are independent, then what is the property of orthogonality? In the range 0 to t, total time period t, which is 4, x2 into x3 should be 0. Do I have that? This is another important property for orthonormal basis function choice. You just check the product of x2 and x3. See, if I multiply this with this, what do I get in the interval 0 to 4? 0 to 2, it is 3 into 0, it will remain 0. And again here 2 to 4 also, it remains 0. So does it satisfy the principle of orthogonality? For these signals to be having orthonormal basis functions, they should satisfy the orthogonality property, that is the integral under the product of the two signals should be 0. They should be orthogonal to each other. Okay. You say is true for the above signals. So for whatever signals are given above, this is surely true. Hence, x2 and x3 are orthogonal to each other. In the, remember the interval is important. In the interval, what? 0 to 4. If you consider shorter interval 0 to 2 and all, they won't be orthogonal to each other. Okay. So once this is decided, to use Gram Schmidt procedure, I have to use Gram Schmidt procedure to find the values of phi1, to find phi1 and phi2. We said there are two orthonormal basis functions and coefficients S11, S21, so on. So let's try to use this procedure. You see how it is done. Understand this clearly. We'll be doing one or two more problems using a similar procedure. In step 1, okay, based on our derivation, in step 1, first, since the signal is given, okay, since we are considering x2 and x3 to be orthogonal to each other, let us try to find the energy content in each of these signals. Energy content of x2 of t, that is E2. How do I find the energy? Integral what? Integral 0 to t x2 square of t dt. Yes or no? That's how you find the energy in a given signal. So what is the time period for which x2 is existing? It is existing in the interval 0 to 2 and the value in that interval is 3. So how should I find this energy? In the interval 0 to 2, 3 square dt. That's all. That is the energy in the signal x2 of t. This is the signal x2 of t. Its amplitude is 3. So x2 square of t will be 3 square and the time interval is between 0 to 2. What is this value? Let me just find out. This 9 comes outside. Integral 1 dt is t in the range 0 to 2. So this will be 9 into, is that right? Yes or no? Any doubts so far? So now we are trying to find the energy E2, which is obtained as the energy in the signal x2, which is defined as integral 0 to t x square t dt. I've just applied the values as given in the waveform and I've got the energy level. Now, do you remember how to find the value of the basis function? What is the definition for basis function phi 1? Therefore, from the Gram Schmidt procedure, the basis function phi 1 of t is defined as the given signal S2 or x2 of t divided by root of its energy. How do I define the signal phi 2 of t? It is defined as a given signal divided by square root of its energy, or in terms of, if you want to write it in terms of the coefficient, it will be S2 of t divided by S21. Anyway, write it like this only, it's easier. So I can write it as x2 of t, the signal, divided by root 18, or x2 of t divided by, can I write it as 3 root 2? Root 18 can be written as 3 root 2. Okay. Can we draw this signal? Now let's draw this signal. Therefore, phi 1 of t is graphically represented as whatever was x2 divided by 3 root 2. What was x2? x2 had the value 3 in the interval 0 to 2. So that 3 should be divided by 3 root 2. What will I get? 3 divided by 3 root 2. So this magnitude will be 1 by root 2. Phi 1 of t is nothing but x2 divided by 3 root 2. So phi 1 of t signal is represented as this square with amplitude 1 by root 2 in the interval 0 to 2. Is that clear? So this is how we represent the signal phi 1, which is one of the orthonormal basis functions in the set. Now I'll continue to find the second orthonormal basis function phi 2, for which we know which is the other linearly independent signal. Consider x3 of t, which is also linearly independent, and find the energy in this signal. Like it is similar to this. I told you, like maths. Like how we considered x2 and found the energy, you have to find the energy in x3 of t. So what is the energy in x3 of t? 0 to t x3 square dt. And this x3 existed from where to where? Look at the signal. x3 is present in the time interval 2 to 4 and its value is 3. Magnitude is 3. So here this exists from 2 to 4 and the magnitude is 3. So 3 square dt. I think you will get 9 into t, and t should be computed for the interval 2 to 4. Will I get the same value? Anybody has computed? Okay. So this will be 9 into 2, which will be 18 only. Correct. So the energy in signal X3 denoted as E3 is also 18. So now I can find the second orthonormal basis function. Therefore, let me call this step 4. Second orthonormal basis function. Second orthonormal basis function phi 2 of t will be, you compute phi 2 of t as x3 of t divided by root of E3. Just like how we computed there, x2 of 2 divided by root E2, x3 divided by root E3, or x3 of t divided by 3 root 2. Again, let's draw that signal. I want to draw the signal phi 2. Remember, this will exist in the interval 2 to 4 because x3 exists in the interval 2 to 4, and the value of this signal would be 3 by 3 root 2. The actual value of x3 was 3 in this range. In this range it was 0. So 0 divided by anything, it will remain as 0. Here 3 divided by 3 root 2, the value turns out to be 1 by root 2. Okay. So this is the representation of the two orthogonal signals in the forming the basis function set of the given signals. Okay. And now we will expressing the given signals, x1, x2 and x3 as a, that is the next question in the problem, as a linear combination of orthonormal basis functions phi 1 and phi 2. We get, tell me what do you get, how do you write? x1 of t can be written as what? What is the x1 of t? Initially only we saw. It is x2 of t plus x3 of t. Yes or no? And what is x2 of t? What can I write x2 of t in terms of phi 1? Look at this equation. Phi 1 is x2 divided by 3 root 2. Therefore, can I say x2 is 3 root 2 into phi 1? Yes or no? Looking at this equation, phi 1 is nothing but x2 divided by 3 root 2, or x2 is 3 root 2 into phi 1. Similarly, what is x3? Similarly, x3 is 3 root 2 into phi 2. Cross multiplying. I am just cross multiplying in this equation. If phi 2 is x3 by 3 root 2, x3 will be, x3 is 3 root 2 into phi 2 by cross multiplying. Now you recall that x1 is a linear combination of x2 and x3. We clearly saw this relation in the beginning itself. Given x1 was like this and x2 and x3 were like this, we could clearly see x1 could be obtained by adding x2 and x3. And I know the expression for x2. I know the expression for x3. So if I substitute that, what will I get? I want to write x1 of t in terms of its orthonormal basis functions phi 1 and phi 2. So x2 is 3 root 2 phi 1 of t and x3 is 3 root 2 phi 2 of t. Therefore, x1 of t is given as 3 root 2 phi 1 of t plus 3 root 2 phi 2 of t. Is that clear? x1 plus x3. Sorry, x1 is x2 plus x3. Similarly, what would be the expression for x2 of t and x3 of t? We already know what is x2 of t. x2 of t is 3 root 2 phi 1 of t. So it will have only the first basis function 3 root 2 phi 1 of t plus 0 into phi 2 of t. Write it like this so that it will be easy for you to write the coordinates. To draw the constellation plot, so what will be the coordinates of signal x1? What are the axes in a constellation diagram? What constitute the axes? These orthonormal basis functions phi 1 and phi 2 form the axis in the constellation diagram. And what would be the coordinates? The coefficient of phi 1 and the coefficient of phi 2. So 3 root 2 comma 3 root 2 would be the what? Coordinates to plot the signal x1. So to plot the signal x1, the coordinates are the coefficients of the basis functions. Similarly, what would be the coordinates of signal x2? It has a coefficient for phi 1, but the coefficient for phi 2 is 0. That's why I'm telling write it in this form. So second term has no meaning here. It is 0 as it is. Similarly, what can I write x3 as? x3 is 3 root 2 phi 2 of t. So it has the second component 3 root 2 phi 2 of t. The first component is absent 0 into phi 1 of t. So what are the coordinates of the point x3? 0 and 3 root 2 will be the coordinates of the point x3. Is that clear? Any doubts? Shreya, do you have any doubt? Shreya, you are unmuted. Please ask if you have any doubt. As I told you, S1, S2, S3 are represented as X1, X2, X3 in this case. We have written the expressions for the signals using the orthonormal basis function as a linear equation, and we have obtained the coordinate values. So can we draw the constellation diagram now? Let's draw the constellation diagram. I think only positive we have, no? We don't have negative values. So remember, one axis should represent one orthonormal basis function. The other axis should represent the other. And these two should be right angled, orthogonal to each other. 90-degree phase shift. Okay? So still people are joining. I don't know why you do this. Now can I represent the signal x1? What are the coordinates for x1? The phi 1 axis is 3 root 2 and the phi 2 axis is also 3 root 2. So if I draw the point, say 3 root 2, this is also 3 root 2. This represents the signal point x1. Okay. So x1 has coordinates 3 root 2 comma 3 root 2. So I'm just finding both the values here and I'm plotting the signal point x1. If you want, you can join it using a straight line. If you want to find the length, sorry. If not, you can just mark the point and leave it. Okay. So how do I represent the signal x2? Its coordinates are the phi1 axis is 3 root 2, the phi2 axis is 0. So where does x2 lie? x2 lies on the x-axis or on the phi1 axis. So this is x2. Its coordinates are 3 root 2 and 0. Is that clear? Similarly, what is x3? It has coordinates 0 and 3 root 2. So it has a y coordinate, but it doesn't have a x value. So it should lie on the y-axis. This is x3, the point 0 and 3 root 2. So this point represents x3, this represents x1, this represents x2. And these are the signals. If I draw the straight lines, they represent the length of the signals x1, x2, x3. Now, is this procedure clear? See, in this problem, we added a little complexity by initially he has only given us 3 signals. He is asking us to find the set of orthonormal basis functions. So first you should determine how many basis functions will be there. Okay, that is dependent on seeing how many linearly independent signals are there. And based on that you can have, if you are going to have two equations, you will be having two different basis functions, orthonormal basis functions. You will express one signal in terms of the other. So this is a dependent signal. Then you should find the values. You can also verify whether the two signals what you considered were independent of each other by checking for the integral under the product, which gives you a measure of orthogonality. If this is 0, then they are orthogonal to each other and they form an orthonormal basis set. Now, using the Gram Schmidt procedure, I'll find the energy in each of the independent signals. You should find the energy in the independent signal and then find the value of the basis function as the signal divided by root of its energy. So the first basis function we got. Similarly, second basis function, the second independent signal, its energy, and the second orthonormal basis function is signal divided by root of its energy. Finally, we will try to write all the three signals as a linear equation of orthonormal basis functions. So we are writing it like this. We get the coordinate points which we will plot on the signal constellation diagram. You can see all the 3 points are lying in the first quadrant only. Is that clear? So all 3 points lie in the first quadrant itself. Any doubts with this? No doubts. Okay, then we'll move on to the next problem. Let's say problem 4. Take down. Given four signals S1, S2, S3 and S4 as described below. Use the Gram Schmidt orthogonalization procedure and find the orthonormal, find the orthonormal basis functions for this set of signals. Also construct the signal space diagram corresponding to this. Okay, the signals are given as follows. S1 of t is 1. In the range t lies between 0 to t by 3. S2 of t will be 1 in the range t by 3 to 2t by 3. S3 of t is 1 in the range t by 3 to complete t, and S4 of t is 1 in the range 0 to t. Okay. This is the definition given for the 4 signals. Let me call this equation 1. Now, first represent each of these signals graphically. Graphical analysis is the simplest and easiest way to analyze in all these problems. So, can we try to represent each of these signals graphically before trying to see how many basis functions will be there and the Gram Schmidt procedure? And when you represent graphically, you will find out how many basis functions, how many linearly independent signals are there. So here S1 is 1 in which range? 0 to t by 3. Okay, if I consider it is 1 in the range 0 to t by 3. This is S1. Let's take S2 here. This is 1 in the range t by 3 to 2t by 3, right? It is 1 in this range as given here. It's 1 in the range t by 3 to 2t by 3. S3 is 1 in the range t by 3 to t. Let me draw S3. This is from where? T by 3 to t, no? Let me consider this as the third part. First part, second part, third part of the signal. T by 3 to t, it is 1. And S4 is 1 completely between 0 to t. S4 of t is 1 in the interval 0 to t. Okay. Now looking at this, can you tell me how many linearly independent signals will be there? Okay, if you compare this, can you express one as the sum of others? Can any one signal in this be dependent on the other signals? Look at these waveforms and tell me. Quickly. Naturally, if you see, looking at the signals, It would be good if you unmute and answer. Yes, S4 can be represented as what? S1 plus S3, right? S4 can be represented as S1 plus S3. So only S4 is dependent. Only S4 is a dependent signal and nothing else can be expressed as a sum of others. You say, therefore, we have three linearly independent signals, that is S1, S2 and S3, right? All the three are linearly independent here. Therefore, we should have how many basis functions? We should have three orthonormal basis functions. Okay. So this determined, I want you to go home and try to find the values of basis functions like how we did previously. Find the energy and find the function. But one thing you should remember, for the first one, it is easy for S1, but S2 and S3 and all, there will be a projection of S1 on S2, S2 on S3 like that. So there will be some dependence which you should see.